In fact, when we are talking about constructing word embedding, it is nothing but just to use vectors to represent words. But these word vectors will be similar to each other when the words have similar meaning or appear in similar contexts. In a nutshell, word vectors are nothing but a series of real numbers that represent the meanings of natural language words. Let's start with a conceptual look at word vectors so that you can get a basic understanding of how to mathematically calculate the semantic similarity between the words represented in the form of vectors. In statistical modeling, you map words to vectors of real numbers that reflect the word's semantic similarity. You can imagine a word vector space as a cloud in which the vectors of words with similar meanings are located nearby. For example, the vector representing the word helicopter should be closer to the vector of the word Jerome than to that of the word eagle. Since the first two refer to machinery, while the latter refers to an animal, to generate these vectors, you need to encode the meanings of these words. Actually, there are a few approaches to encoding meaning. One way to generate meaningful word vectors is by assigning an object or category from the real world to each coordinate of a word vector. For example, suppose you are generating word vectors for the following words: helicopter, Jerome, goose, eagle. The word vectors should mathematically reflect the fact that all of them are flying in the sky. At the same time, they should also reflect the fact that helicopter and Jerome are machinery, while goose and eagle are animals with wings. Here, we distribute the meaning of each word between its coordinates in a three-dimensional space, representing the categories sky, engine, and wings. In this simplified example, a coordinate value can be somewhat arbitrary values, indicating whether or not a corresponding word belongs to that category. Once you have a vector space in which vectors of numbers capture the meaning of the corresponding words, you can use vector arithmetic on this vector space to gain insight into the word's meaning. Word2Vec is a technique for natural language processing published in 2013. The Word2Vec algorithm uses a neural network model to learn word association from a large corpus of text. Once trained, such a model can detect synonymous words or suggest additional words for a partial sentence. As the name implies, Word2Vec represents each distinct word with a particular list of numbers called a vector. The vectors are chosen carefully such that a simple mathematical function, the cosine similarity between the vectors, can indicate the level of semantic similarity between the words represented by those vectors. Word2Vec is a group of related models that are used to produce word embeddings. These models are shallow, two-layer neural networks that are trained to reconstruct linguistic context of words. Word2Vec takes a large corpus of text as its input and produces a vector space, typically of several hundred dimensions, with each unique word in the corpus being assigned a corresponding vector in the space. Word vectors are positioned in the vector space such that words that share common context in the corpus are located close to one another in the space. Word2Vec can utilize either of two model architectures to produce a distributed representation of words: continuous bag of words or continuous skipgram. In the continuous bag of words architecture, the model predicts the current word from a window of surrounding context words. The order of context words doesn't influence prediction. In the continuous skipgram architecture, The model uses the current word to predict the surrounding window of context words. The skip-gram architecture weights nearby context words more heavily than more distinct context words. According to the Google's research, continuous backup words is faster, while skip-gram does a better job for infrequent words. Word2Vec is a method to efficiently create word embeddings and has been around since 2013. In addition to its utility as a word embedding method, some of its concepts have been shown to be effective in creating recommendation engines and making sense of sequential data even in commercial, non-language tasks. Companies like Airbnb, Alibaba, Spotify have all benefited from carving out this brilliant piece of machinery from the world of NLP and using it in production to empower a new breed of recommendation engines. As we mentioned earlier, Word2Vec is an algorithm that helps us build distributed representation automatically. The algorithm represents every word in our fixed vocabulary as a vector. Word2Vec identifies a center word and its context and outside words. Then, it uses the similarity of the word vectors for center word and context to calculate the probability of context, given the center word. Finally, the tool optimizes the vector by maximizing this probability. So, how can we go from individual probability calculations to a single equation for the entire model? Let's look at this example of a sentence. Problem turning into banking crisis as blah blah blah. We want to calculate the probability of all the outside words for the word banking. To start, let's refer to banking at the current position in the text T. Our center word C is banking. To make calculating the probability easier, we refer to this center word C as WT. Assuming we are using a window size of 2, our context words are the words that position T-2, T-1, T+1, and T+2. Written another way, those are WT-2, WT-1, WT+1, and WT+2. Now, you can express the probability of the outside words, giving a center word as POC. So at position T-2, the probability would be P WP-2 given WT, and so on. From these individual probabilities, you can write a single equation for the probability over all the data. There are two types of model for Word2Vec, as we mentioned earlier. They are skip-gram and continuous backup words. Both are architectures to learn the underlying word representation for each word by using neural networks. In the continuous backup words model, the distributed representation of context or surrounding words are combined to predict the word in the middle, while in the skip-gram model, the distributed representation of the input word is used to predict the context. A prerequisite for any neural network or any supervised training technique is to have labeled training data. How are we going to train a neural network to predict word embedding when we don't have any labeled data? That is, words and their corresponding word embedding. We will do so by creating a fate task for the neural network to train. We won't be interested in the input and output of this network. Rather, the goal is actually just to learn the weight of the hidden layers that are actually the word vectors that we are trying to learn. The fate task for skip-gram model would be, given a word, we will try to predict its neighboring words. We will define a neighboring word by the window size, which is a hyperparameter. The dimensions of the input vector will be 1 times v. where V equals to the number of unique words in the vocabulary. That is one hot encoding of the word. The single hidden layer will have dimension V times n, where n is the size of the word embedding and is a hyperparameter as well. The output from the hidden layer would be of dimension 1 times n, which we will feed into a softmax layer. The dimensions of the output layer will be 1 times v, where each value in the vector will be the probability score of the target word at that position. The backpropagation for training samples corresponding to a source word is done in one backpropagation. So for a center word, we will complete the forward pass for all 4 target words. We will then calculate the errors vectors corresponding to each target word. We will now have 4 error vectors and will perform an element-wise sum to get a 1 times v vector. The weights of the hidden layer will be updated based on this cumulative error vector. Skip-gram model works well with a small amount of the training data, represent well even rare words or phrases. The continuous back-of-words model architecture tries to predict the current target word or the center word based on the source context words. The fate task in continuous back-of-word is somewhat similar to skip-gram, in the sense that we still take a pair of words and to teach the model that they co-occur, but instead of adding the errors, we add the input words for the same target word. The dimension of our hidden layer and output layer will remain the same. Only the dimension of our input layer and the calculation of hidden layer activations will change. If we have 4 contexts for a single target word, we will have 4 1 times v input vectors. Each will be multiplied with the v times n hidden layer, returning 1 times n vectors. All 4 1 times n vector will be averaged element-wise to obtain the final activation, which will then be fed into the softmax layer. Continuous back-of-word model is several times faster to train than the skip-gram, and it has slightly better accuracy for the frequent words. To sum up, there are 2 ways to implement word embeddings using word-to-vec: continuous back-of-words and skip-gram. Continuous back-of-words model learns to predict a target word given a context word, while skip-gram model learns to predict a context for a given center word, exactly the opposite of the continuous back-of-words model. When we compare the 2 model variants, continuous back-of-words model is faster and more efficient on memory, but the drawback is it takes the average of context of a word. For example, the word apple. It can be a fruit, or it can also be a company name, but CBOW model cannot distinguish that. For skip-gram model, it works well with small amount of training data and is found to represent rare words really well. Skip-gram model can also capture 2 semantics of a single word, such as apple. However, skip-gram model is less efficient in training. That means a longer training time is required. It seems like when their vectors are not average with the other background terms in the process of making predictions, the model will learn better representation for the rare words, and it is better to use skip-gram model in that case. At the end, since different applications have distinct criteria, the best practice is to try a few tests to see what works best for the application. Last but not least, there are also other word embedding models that are even better than word-to-vec. While word-to-vec model only takes local context into consideration, but it does not take advantage of global count statistics. Therefore, there is a more advanced model, GLAF, that was developed by Stanford University in 2014. GLAF is short for global vectors. In depth, the GLAF model is used for the representation of the distributed words. This model represents words in the form of vectors using an unsupervised learning algorithm. This unsupervised learning algorithm maps the word into space where the semantic similarity between the words is observed by the distance between the words. The algorithm performs the training of a corpus consisting of the aggregated global word co-occurrence statistics, and the result of the training usually represents the subspace of the words in which our interest lies. The model has been trained using 6 billion tokens, 400,000 vocabularies into vector with different dimensions. Similar to word2vec, global vectors use window around each word, and it captures both syntactic and semantic information. For example, all animal terms will have similar entries. In practice, word2vec employs negative sampling by converting the softmax function as the sigmoid function. This conversion results in cone-shaped clusters of the word in the vector space, while global vectors are more discrete in the space, which makes the word2vec model faster in the computation than the global vectors.